We have already seen how to apply the first law of thermodynamics for an ideal gas. Now we will examine the heat exchange in different thermodynamic processes for an ideal gas. All the state variables of an ideal gas, that is its pressure, volume, and temperature, change in general thermodynamic processes. However, if we assume that the process is quasi-static, then the state variables are still related by the equation of state for a given amount of ideal gas. In other words, the ideal gas law holds throughout the process, that is the pressure P of the gas times its volume V is equal to the amount N of the substance, times the gas constant R, times the absolute temperature T of the gas. In quasi-static processes, the equation of state for an ideal gas represents a constraint connecting the state variables to each other, and each state variable can be expressed in terms of the other two variables. In a general thermodynamic process, an ideal gas exchanges heat with the surroundings and does work on the surroundings, or the surroundings do work on the gas. In both cases, the state of the gas changes, therefore the internal energy and the enthalpy of the gas change as well. We have already studied the change in the state of an ideal gas in some important cases, where the state variables satisfy a given condition throughout the thermodynamic process. An isothermal process is such an important process, where the temperature of the gas is constant. Here are some examples as a reminder. Typical isothermal processes in nature are the melting of ice and the boiling of water, since the phase transitions take place at constant temperature. A refrigerator also works isothermally. Although a set of changes take place in the thermodynamic cycle of a refrigerator, the temperature inside remains constant. The first step of the operating cycle of Carnot heat engines is also an isothermal expansion of gas in the cylinder of the engine. An isobaric process is another important thermodynamic process, where the pressure of the gas is constant. Melting and boiling are also isobaric processes, since the phase transitions of water take place at constant pressure. An isobaric process takes place in hot air balloons as well. When the gas in the balloon is heated, it increases its volume and keeps its pressure constant. A steam engine is also a typical example for such a process, where the water entering the boiler of a steam engine is heated to its boiling point, vaporized, and then the steam is superheated. All these processes take place isobarically in the engine. The third type of the important thermodynamic processes is an isochoric process, where the volume of the gas is constant. An obvious example from the real life is cooking in the pressure cooker. If its valve is still closed, then it keeps the pressure constant in the cooker. The working principle of constant volume calorimeters is also based on the isochoric change in the thermodynamic state of the substance placed in the sample chamber of the device. Another example is the diesel engine, where the last step in its operating cycle is an isochoric depressurization in the cylinder of the engine. We will examine the heat exchange in these types of processes, but we also introduce another one, called adiabatic process, where the heat exchange between the system and the surrounding is forbidden. In nature, adiabatic cooling is the process where the humidification of air results in cloud formation. The operation of gas turbines can also be approximated as adiabatic expansion of the gas, where the hot combustion gas expanding through the turbine spins the rotating blades. In fire syringes, a rapid adiabatic compression of the air in its cylinder causes the temperature of the gas to rise rapidly, which ignites the material at the base of the cylinder, resulting in a bright flash. Let us start our study on the conversion of heat with a quasi-static isothermal process in an ideal gas. We can imagine a cylinder filled with an ideal gas and sealed by a moving piston. In the initial state of this thermodynamic system, the gas has the pressure P1, the volume V1, and the absolute temperature T as its initial state variables. The gas absorbs the amount Q of heat from the surroundings in a quasi-static process, and we assume that it will have an isothermal expansion, that is, its temperature remains constant. As a result, the gas will have the pressure P2 and the volume V2 in its final state, whereas its temperature is still equal to its initial temperature T. At the same time, the expanding gas does the pressure volume work W' on the surroundings by moving the piston. In the case of an isothermal process, the equation of state for a given amount of ideal gas reduces to Boyle's law, stating that the product P of the gas and its volume V is constant. For a given absolute temperature T, this constant is equal to the amount N of the substance, times the gas constant R, times the absolute temperature T. This law is represented by the parametric set of isotherms in the state space, where the parameter is the absolute temperature of the gas. These isotherms are rectangular hyperbolas in the pressure versus volume diagram. We can also see in the diagram how the state of the system evolves from its initial state with the pressure P1 and the volume V1 to its final state with the pressure P2 and the volume V2 along an isotherm for the given temperature T. Boyle's law provides the relationship between the state variables in the initial and the final states of the gas, telling that the pressure P1 times the volume V1 is equal to the pressure P2 times the volume V2, or the ratio of the pressure P1 to the pressure P2 is equal to the ratio of the volume V2 to the volume V1. The first law of thermodynamics states that the heat Q absorbed by the gas is equal to the change U2 minus U1 in its internal energy, minus the work W done on the gas, or plus the work W prime done by the gas. Since the internal energy U of an ideal gas is given by its mass m times its specific heat capacity CV for a constant volume times its absolute temperature T, the internal energy is directly proportional to the absolute temperature. As a result, the internal energy of the ideal gas is the same in the initial and the final states of an isothermal process. That is, the internal energy U1 of the gas in its initial state is equal to its internal energy U2 in its final state. Since the change in the internal energy of the gas is zero in an isothermal process, the total amount of heat absorbed by the gas is converted into the pressure volume work done by the gas, that is the heat Q is equal to the work W prime. Then the heat Q and the pressure volume work W prime are given by the integral of the pressure P of the gas with respect to the volume V from the initial volume V1 to the final volume V2. If we substitute the ideal gas law into the integral, then we obtain the amount N of substance, times the gas constant R, times the temperature T, times the integral of 1 over the volume V with respect to the volume V from the initial volume V1 to the final volume V2. By performing the integration, we obtain N times R times T, times the natural logarithm of the ratio of the final volume V2 to the initial volume V1. If we apply Boyle's law in the form expressed under the pressure versus volume diagram, then the Q heat and the work W prime can be written as the amount N of substance, times the gas constant R, times the absolute temperature T, times the natural logarithm of the ratio of the initial pressure P1 to the final pressure P2. This result demonstrates that the heat Q absorbed and the work W prime done by the gas are positive for the expansion of the gas, and negative for the compression of the gas. In the case of compression, the work W done on the gas is equal to minus W prime, and the gas releases the same amount of heat Q to the surroundings. The second type of thermodynamic process in an ideal gas is the isochoric process, where the volume of the gas is constant. Let us consider a closed container with the volume V, which is filled with an ideal gas. Let P1 and T1 denote the initial pressure and temperature of the gas, respectively. If the gas absorbs the amount Q of heat from the surroundings in a quasi-static process, then its temperature will increase. Since the gas is confined in the container with a fixed wall, it cannot expand and its pressure will increase as well. The final pressure and temperature of the gas are denoted by P2 and T2. In the case of isochoric processes, the equation of state for a given amount of ideal gas reduces to Gay-Lussac's law stating that the pressure P of the gas is directly proportional to the absolute temperature T of the gas. The proportionality constant is given by the amount N of the substance times the gas constant R, divided by the constant volume V of the gas, which can be written as the mass m times the specific gas constant Rs, divided by the volume V. This law is represented by the parametric set of isochors in the state space, where the parameter is the volume of the gas. These isochors are lines in the pressure versus temperature diagram. We can also see in the diagram how the state of the system evolves from its initial state with the pressure P1 and the temperature T1 to its final state with the pressure P2 and the temperature T2 along an isochor for the given volume V. Gay-Lussac's law provides the relationship between the state variables in the initial and the final states of the gas, telling that the ratio of the pressure P1 to the temperature T1 is equal to the ratio of the pressure P2 to the temperature T2. The slope of each isochor is inversely proportional to the volume V of the gas. We have already seen that the first law of thermodynamics applied for isochoric processes tells us that the heat absorbed by the gas increases the internal energy of the gas, since the gas does not do any pressure volume work. As a result, the total amount of heat absorbed by the ideal gas increases the internal energy of the gas. That is, the heat Q is equal to the difference between the internal energy U2 of the gas in its final state and the internal energy U1 of the gas in its initial state. The internal energy U of a given amount of ideal gas is equal to the mass m of the gas, times its specific heat capacity CV measured in an isochoric process, times its absolute temperature T. By substituting this expression into the first law, we obtain the following expression: the mass m times the specific heat capacity CV, times the difference between the final temperature T2 of the gas and its initial temperature of T1. If we insert Gay-Lussac's law into this result, then we can write that the heat Q absorbed by the gas is equal to the ratio of the specific heat capacity CV of the gas for a constant volume to the specific gas constant Rs of the gas, times the volume V of the gas, times the difference between its final pressure P2 and its initial pressure P1. Now we can conclude that in an isochoric process, the heat absorbed by an ideal gas is directly proportional to the change in its temperature and its pressure. This result demonstrates that the heat Q absorbed by the gas is positive for heating, where both the temperature and the pressure of the gas increase. The heat Q is negative for cooling, where both the temperature and the pressure of the gas decrease. The third type of thermodynamic process in an ideal gas is the isobaric process, where the pressure of the gas is constant. As in the case of the isothermal process, we consider a cylinder filled with an ideal gas and sealed by a moving piston. In the initial state of this thermodynamic system, the gas has given absolute temperature, volume, and pressure denoted by T1, V1, and P respectively. If the gas absorbs the amount Q of heat from the surroundings in a quasi-static process, then it will expand and its temperature increases, whereas its pressure remains constant. As a result, the gas will have the temperature T2, the volume V2 in its final state, whereas its pressure is still equal to its initial pressure P. At the same time, the expanding gas does the pressure volume work W' on the surroundings by moving the piston. In the case of isobaric processes, the equation of state for a given amount of ideal gas reduces to Charles's law stating that the volume V of the gas is directly proportional to the absolute temperature T of the gas. The proportionality constant is given by the amount N of the substance times the gas constant R, divided by the constant pressure P of the gas, which can be also written as the mass M of the gas times its specific gas constant Rs, divided by the gas pressure P. This law is represented by the parametric set of isobars in the state space, where the parameter is the pressure of the gas. These isobars are lines in the volume versus temperature diagram. We can also see in the diagram how the state of the system evolves from its initial state with the volume V1 and temperature T1 to its final state with the volume V2 and the temperature T2 along an isobar for the given pressure P. Charles's law provides the relationship between the state variables in the initial and the final states of the gas, telling that the ratio of the volume V1 to the temperature T1 is equal to the ratio of the volume V2 to the temperature T2. The slope of each isobar is inversely proportional to the pressure P of the gas. We have already seen that the first law of thermodynamics applied for an isobaric process tells us that the heat Q absorbed by the gas is equal to the difference between the enthalpy H2 of the gas in its final state and the enthalpy H1 of the gas in its initial state, since no technical work is done at a constant pressure. Then the total amount of the heat absorbed by the gas increases the enthalpy of the gas, that is, the heat Q is equal to the difference between the enthalpy H2 and the enthalpy H1. The enthalpy of an ideal gas can be written as the mass M of the gas, times the specific heat capacity Cp of the gas for a constant pressure, times the absolute temperature T of the gas. By substituting this expression into the first law, we obtain the following expression: the mass M times the specific heat capacity Cp, times the difference between the final temperature T2 of the gas and its initial temperature T1. If we insert Charles's law into this result, we can write that the heat Q is equal to the ratio of the specific heat capacity Cp for a constant pressure to the specific gas constant Rs, times the pressure P of the gas, times the difference between its final volume V2 and its initial volume V1. Now we can conclude that in an isobaric process, the heat absorbed by an ideal gas is directly proportional to the change in its temperature and its volume. This result demonstrates that the heat Q absorbed by the gas is positive for heating, where both the temperature and the volume of the gas increase. The heat Q is negative for cooling, where both the temperature and the volume of the gas decrease. Now we introduce the concept of thermal efficiency, measuring the fraction of heat absorbed by a thermodynamic system that becomes useful work. We denote thermal efficiency by eta, and define it as the ratio of the work done by the system to the heat delivered to the system. Let us suppose that the working substance in the system is an ideal gas, the heat Q is delivered to the gas and the pressure volume work W' is done by the gas. Then the thermal efficiency eta of a thermodynamic process in the gas can be written as the ratio of the work W' done by the gas to the heat Q absorbed by the gas. For an isobaric process in an ideal gas, the heat Q absorbed by the gas is given by the ratio of the specific heat capacity Cp of the gas to its specific gas constant Rs, times the pressure P of the gas, times the difference between its final volume V2 and its initial volume V1. The pressure volume work W' done by the gas is equal to the pressure P times the difference between the volume V2 and the volume V1. By substituting these expressions into the definition of thermal efficiency, we can write eta as the specific gas constant or S divided by the specific heat capacity Cp of the gas for a constant pressure. If we apply Meyer's relation stating that the difference between the specific heat capacity Cp of an ideal gas for a constant pressure and its specific heat capacity Cv for a constant volume is equal to its specific gas constant Rs, then we can express eta as the difference between Cp and Cv divided by Cp. By dividing both the numerator and the denominator of the fraction by Cv, we obtain an expression that depends only on the ratio of the heat capacities. We can introduce the heat capacity ratio or the adiabatic index of a substance as the ratio of its specific heat capacity Cp for a constant pressure to its specific heat capacity Cv for a constant volume. As its name indicates, this quantity is just the ratio of the heat capacity Cp for a given amount of substance measured at constant pressure, to its heat capacity Cv measured at a constant volume, since the mass of the substance cancels out in the fraction. Then we obtain that the thermal efficiency eta for an ideal gas in an isobaric process is equal to the ratio of gamma minus 1 to gamma. We note that the heat capacity ratio can be determined for any ideal gas in statistical mechanics. It can be shown that gamma is equal to 5/3 for a monatomic ideal gas, and 7/5 for a diatomic ideal gas. Since the air can be considered as a mixture of diatomic ideal gases, its adiabatic index is about 7/5. Then the thermal efficiency of an isobaric process in a thermodynamic system using air as a working substance is somewhat less than 30%. The last type of thermodynamic process is an ideal gas, which we discuss here is the adiabatic process. By definition, in an adiabatic process there is no heat exchange between the thermodynamic system and in the surroundings. Any thermodynamic process undergoing in a system can be considered as an adiabatic one, if the boundary of the system is an adiabatic wall preventing the exchange of heat between the two sides of the wall. In other words, an adiabatic process can take place in any system with thermal insulation reducing the heat flow to a large extent between the system and its environment. Here we can consider an thermally insulated cylinder filled with an ideal gas and sealed by a piston. Since perfect thermal insulation does not exist, we can only talk about an adiabatic approximation of the processes in thermally insulated systems. However, if the change in the state of the system occurs rapidly enough, there is no time for a considerable exchange of heat between the system and the surroundings. Then we can apply the adiabatic approximation, as in the case of fire syringes, where the compression of the air in the cylinder is so fast that the heat produced by the compression of air cannot escape, and ignites the material in the cylinder. However, such a process cannot be studied in the quasi-static approximation, since the air does not remain in thermodynamic equilibrium during the rapid change in its state. Instead, we consider an adiabatic compression in the thermally insulated cylinder, where the initial temperature, volume and pressure of the gas are denoted by T1, V1 and P1, respectively. If the gas is compressed in the cylinder by the moving piston, then the pressure volume work W can be done on the gas without the exchange of the heat Q between the thermally insulated cylinder and the surroundings. In the case of quasi-static adiabatic compression, the slowly moving piston compresses the gas and it changes its thermodynamic state. The final temperature, volume, and pressure of the gas are denoted by T2, V2 and P2, respectively, where the volume V1 is greater than the initial volume V2. The first law of thermodynamics applied for an ideal gas states that the internal energy U2 of the gas in its final state, minus its internal energy U1 in the initial state is equal to the heat Q absorbed by the gas plus the work W done on the gas. Since the heat exchange Q is 0 in the adiabatic compression, the total work done on the gas increases the internal energy of the gas, that is the work W is equal to the difference U2 minus U1 in its internal energy. For a given amount of ideal gas, we can substitute the expression mass m of the gas, times its specific heat capacity Cv for a constant volume, times its absolute temperature T into the internal energy U of the gas in the right-hand side of the equation. Then the work W done on the gas and the change in its internal energy U can be written as the mass m times the heat capacity Cv, times the difference between the final temperature T2 of the gas and its initial temperature T1. Since the work W done on the gas is positive, the gas warms up in the adiabatic compression. In the case of adiabatic expansion, an ideal gas does pressure volume work which decreases its internal energy, and the gas cools down. If we apply the differential form of the first law of thermodynamics for an infinitesimal change in the state of an ideal gas, we can write that the differential of the heat Q absorbed or released by the gas is equal to the differential of its internal energy U, minus the infinitesimal pressure volume work W done on the gas. Here the pressure volume work is given by minus the pressure P of the gas, times the differential of its volume V. Since dQ vanishes in the adiabatic process, the first law tells us that the differential of the internal energy U, plus the product of the pressure P and the differential of the volume V vanishes. The infinitesimal change in the internal energy U for a given amount of ideal gas is equal to the mass m of the gas, times its specific heat capacity Cv for a constant volume, times the infinitesimal change in its absolute temperature T. The pressure P can also be expressed from the ideal gas law as the mass m of the gas times its specific gas constant Rs, times its absolute temperature T divided by its volume V. If we substitute Meyer's relation into this equation, then we obtain that the pressure P is equal to the mass m times the difference between the specific heat capacity Cp and Cv, times the absolute temperature T divided by the volume V. We can insert these expressions into the differential form of the first law, which gives the following equation. The mass m times the specific heat capacity Cv times the differential of the temperature T, plus the mass m times the difference between the specific heat capacities Cp and Cv, times the absolute temperature T, times the differential of the volume V divided by the volume V, is equal to 0. If we divide this equation by m times Cv times T, then we obtain the following expression. The differential of the temperature T divided by the temperature T, plus the heat capacity ratio gamma minus 1, times the differential of the volume V divided by the volume V, is equal to 0. By integrating this separable differential equation, we find that the natural logarithm of the absolute temperature T, plus gamma minus 1 times the natural logarithm of the volume V is constant. Then we can write that the natural logarithm of T times V to the power of gamma minus 1 is constant, which tells us that the absolute temperature T times the volume V to the power of gamma minus 1 is constant. Now we can apply the ideal gas law for a given amount of gas, stating that the pressure P of the gas times its volume V is equal to the amount N of substance times the gas constant R, times the absolute temperature T of the gas. Since N times R is a constant for a given amount of ideal gas, we can express the volume V as a constant times T over P, and substitute it into the expression T times V to gamma minus 1, which is constant. Then we obtain a constant times T, times the ratio of T to P raised to the power of gamma minus 1. This gives a constant times T to gamma, divided by P to gamma minus 1. Since the left-hand side of the first equation is constant, we can conclude that the expression T to gamma divided by P to gamma minus 1 is constant. We can also express the absolute temperature T from the ideal gas law as a constant times the product of P and V, and substitute it into the expression T times V to gamma minus 1. Then we obtain a constant times P times V, times V to gamma minus 1. This gives a constant times P times V to gamma. Since the left-hand side of the first equation is constant, we can conclude that the product of P and V to gamma is constant. As a result, we have obtained the functional relations for the state variables of a given amount of ideal gas, when the gas changes its thermodynamic state in an adiabatic process. These three relations are known as Poisson's equations, where the first one states that the absolute temperature T of the gas times its volume V raised to the power of the adiabatic index gamma of the gas minus 1 is constant. The second one tells us that the absolute temperature T to gamma, times the pressure P of the gas raised to the power of 1 minus gamma is constant. The third one states that the pressure P times the volume V to gamma is constant. Sometimes only the third equation is called Poisson's equation in the textbooks on thermodynamics. When we derived these equations from the first law and the ideal gas law, the amount N of the species was absorbed into the constants in the right-hand side of these equations. If we change the amount of species, that is either the amount of the gas or the type of the gas, or both, then these constants will change as well. Since the adiabatic index for a given gas is just the heat capacity ratio of the gas, it also depends on what type of gas goes under in the adiabatic process. Therefore, Poisson's equations provide different functional relations for different amount and types of gases. As an example, we can show Poisson's equations for a monatomic gas that has a heat capacity ratio of 3/5. Then the exponent gamma minus 1 in its Poisson's equations is equal to 2/5. In the case of a diatomic gas, the adiabatic index is equal to 7/5. Thus we obtain different Poisson's equations for a diatomic gas, where gamma minus 1 is equal to 2/5. Poisson's equation describing the functional relation between the pressure and the volume of a given amount of ideal gas in an adiabatic process is represented by curves called adiabats in the pressure versus volume diagram. Let us compare the properties of adiabats and isotherms in the state space of an ideal gas. Boyle's law states that the product of the pressure P and the volume V of a given amount of ideal gas is constant in an isothermal process. We can express the pressure P from Boyle's law as some constant C divided by the volume V. Then the partial derivative of the pressure P with respect to the volume V at a constant temperature can be calculated by taking the derivative of the constant C over the volume V. This gives minus C over V squared, which is equal to minus the ratio of the pressure P to the volume V. In the case of an adiabatic process, Poisson's equation states that the pressure P of the gas times its volume V to the adiabatic index gamma is constant. If we express the pressure P from this equation, we obtain a constant C prime divided by the volume V to gamma. The partial derivative of the pressure P with respect to the volume V for an adiabatic process, that is for the vanishing transfer of the heat Q, is the derivative of C prime divided by the volume V to gamma. This gives minus gamma times C prime over V to gamma minus 1, which is equal to minus the adiabatic index gamma times the ratio of the pressure P to the volume V. If we compare this result with the expression obtained for the isothermal process, we can see that it is equal to gamma times the partial derivative of the pressure P with respect to the volume V at a constant temperature. It can be shown that the adiabatic index gamma is greater than 1 for any substance, not only for an ideal gas. As a result, the tangent of the pressure P as a function of the volume V is greater for an adiabatic process than for an isothermal process in the same thermodynamic state, which can be illustrated as follows. Here we can see the surface and the state space of an ideal gas representing the ideal gas law. The three-dimensional state space is spanned by the axes of the state variables pressure P, volume V and the absolute temperature T of the gas. In the pressure-volume-temperature space, Boyle's law is represented by a set of isochors, which are the section of constant temperature planes with the surface of the ideal gas law. These isochors can be projected onto the pressure-volume diagram, where they form a family of rectangular hyperbolas. If we choose an arbitrary state on one of the isochors represented by the point P in the state space, that can also be projected onto the pressure-volume plane. In the pressure-volume-temperature space, Poisson's equations are represented by adiabats over the surface of the ideal gas law. We plot only one adiabat passing through the point P, demonstrating that all the three state variables of the gas change in an adiabatic process, whereas Poisson's equations represent the constraints imposed on the values of the pressure, the volume, and the temperature of the gas. If we project the adiabat onto the pressure-volume plane, we can see two different curves passing through the point P. Here we can see a set of isochors with the thermodynamic state represented by the point P in the pressure-volume diagram for a given amount of ideal gas. We also plot an adiabat passing through the point P. The slope of the isochor in the state represented by the point P, that is the tangent of the curve in that point, is given by the partial derivative of the pressure P of the gas with respect to its volume V at a constant temperature. Similarly, the slope of the adiabat in the point P is determined by the partial derivative of the pressure P of the gas with respect to its volume V for a vanishing heat flux Q. As demonstrated above, the tangent of the adiabats are greater than the tangent of isotherms in the same state, or in the same point in the state space. Then we can conclude that the slope of adiabats are greater than the slope of isochors in the same state of the gas, that is in any point in the pressure-volume diagram of an ideal gas. We will finish the discussion on adiabatic processes with their application, which helps us to derive the formula for the speed of sound. We have seen that if an adiabatic process takes place in a given amount of ideal gas, then Poisson's equation holds, stating that the pressure P of the gas time its volume V to the adiabatic index gamma is constant. Since the volume of the gas can be expressed as its mass m divided by the density ρ, we can insert this ratio into the equation. Here the mass m and the adiabatic index are constant, therefore we can divide the equation by m to gamma, and absorb it into the constant in the right-hand side. As a result, we can write that the pressure P of the gas times its density ρ to minus gamma is constant. Since the right-hand side of the equation is constant, the differential of P times ρ to minus gamma vanishes. If we apply Leibniz's rule for the differential in the left-hand side of the equation, then we can expand it as the differential of P times ρ to minus gamma times P, times ρ to minus 1 minus gamma, times the differential of ρ. By multiplying out ρ to minus gamma, we obtain ρ to minus gamma times the quantity of dP minus gamma times P times ρ to minus 1 times d ρ, which must vanish. Since ρ to minus gamma is not zero, the differential can only vanish if the terms in the parentheses vanish, that is dP minus gamma times the ratio of P to ρ, times d ρ is equal to 0. This result can be summed up in the differential equation stating that the adiabatic index gamma times the ratio of the pressure P to the density ρ is equal to the derivative of the pressure P with respect to the density ρ. By applying the chain rule, the derivative can be written as the derivative of the pressure P with respect to the volume V, times the derivative of the volume V with respect to the density ρ. Since the volume V of the gas is just the ratio of the mass m of the gas to its density ρ, we obtain minus the derivative of the pressure P with respect to the volume V, times the ratio of the mass m to the density ρ squared. This gives minus the derivative of the pressure P with respect to the volume V, times the ratio of the volume V to the density ρ. If we invert the derivative, we obtain the differential equation stating that 1 over the adiabatic index gamma times pressure P is equal to minus 1 over the volume V, times the derivative of the volume V with respect to the pressure P. In addition, we will use another expression to derive the speed of sound in adiabatic approximation. Since the ideal gas law states that the pressure P of the gas times its volume V is equal to its mass m times its specific gas constant Rs, times its absolute temperature, we can express the pressure P as m times Rs times the ratio of T to V. The right-hand side of the equation is equal to the gas constant Rs, times the density ρ, times the absolute temperature T, which gives the equation stating that the ratio of the pressure P to the density ρ is equal to the specific gas constant Rs times the absolute temperature T. As already mentioned, adiabatic processes are related to the measurement of the speed of the sound in ideal gases. While Newton assumed that the propagation of sound in the air is an isothermal process, Laplace argued that the process is adiabatic. Indeed, the changes in the pressure and the density of the gas during the propagation of the sound wave are fast enough to prevent the exchange of the heat between the volume elements of the gas at the wave front and the surrounding medium. Therefore, the adiabatic approximation provides a better description of the phenomenon. The result derived here can be used to determine the speed of sound in an ideal gas, if we introduce the adiabatic compressibility of substances. As we did for an ideal gas in an isothermal process, we can introduce the adiabatic compressibility of an ideal gas in an adiabatic process. The adiabatic compressibility kappa ad is defined by minus 1 over the volume V of the gas, times the partial derivative of the volume V with respect to the pressure P of the gas for the vanishing heat flow Q. Since the differential equation obtained above was derived for an adiabatic process, we can immediately write the adiabatic compressibility of an ideal gas as 1 over the adiabatic index gamma times the pressure P of the gas. We already defined the isothermal compressibility of an ideal gas by minus 1 over the volume V of the gas, times the partial derivative of its volume V with respect to its pressure P for a constant temperature. When we determined its value, we obtained 1 over its pressure P. Therefore, the adiabatic compressibility kappa ad can be written as the ratio of the isothermal compressibility kappa to the adiabatic index gamma. Since gamma is greater than 1, the adiabatic compressibility of an ideal gas is always smaller than its isothermal compressibility. Now we can express the speed of sound in terms of the adiabatic compressibility, where the square of the speed of sound Cs is defined by the partial derivative of the gas pressure P with respect to its density ρ for an adiabatic process. If we apply the differential equation derived from Poisson's equation, we can write the square of the speed of sound as gamma times the pressure P over the density ρ. This formula differs in the multiplicative factor gamma from the one derived by Newton for isothermal processes. Since the adiabatic index is greater than 1, the sound waves propagate faster in the adiabatic approximation than in the isothermal description. By substituting the expression obtained for the adiabatic compression into this equation, we obtain 1 over the adiabatic compression kappa ad times the density ρ for Cs squared. We can also apply the equation obtained from the ideal gas law, and write the square of the sound speed as the adiabatic index gamma, times the specific gas constant R, times the absolute temperature T of the gas.